KL divergence. KL divergence. So this is coming from the name of two scientists, Kullback and I think Leibler. Divergence. Divergence measures that what is the extra surprise when using a different model to predict, okay, to make predictions. So I'll give you the formula, then you'll understand. So I'm telling you in words. What is this? Is telling me what is extra surprise. So there'll be inherent surprise, that is the entropy, plus what is extra surprise when I am measuring that same entropy using some other model. So what is the difference in both the surprises? That's what KL divergence measures. Okay, extra surprise when using a different model or a different distribution probability in terms of to make predictions. This is very in simple terms. Instead of using the true distribution. Using a true distribution. So I'm using a different distribution. Say this is my Q and the original distribution was P. So what is the extra surprise? What is the delta between the entropy and the cross entropy? So this is your KL. So this is written as. So in other words, if I say this is the difference between the actual surprise which I got using cross entropy. This is the actual surprise that my model predicted, and what was the true value. So this was the actual surprise, and KL divergence measures the difference between this actual surprise minus minimum possible surprise. That's the inherent entropy in that distribution. Okay, so this measures. So let me write it down. So this is written as DKL. Let me use a different color. KL divergence. This is how we write it. Of two distributions P and Q, KL divergence of two distributions P and Q is equal to the cross entropy minus the entropy. Okay, so this is your KL divergence. This is your cross entropy, the actual surprise, and this is the minimum surprise. This is your entropy. This is the minimum surprise that is inherent in the system, and this is the cross entropy that my distribution was something else, but I'm trying to predict it using something else, which is my model. So this is my cross entropy, and the difference between two gives me the KL divergence, that how much extra surprise we have got because of the model or the new distribution, because of that I'm using to measure the true distribution. Okay, so this, in other words, if you say in terms of information, it quantifies the information loss. Okay, whatever the information was there actually in the system. Okay, and what I did using this, what I calculated using this cross entropy or another model or another distribution. So it quantifies this information loss. The information loss, actual, the minimum information loss, and plus the minimum information that it has, and what the new distribution or the model is able to capture. So this is the loss in information. This is the delta that KL divergence tries to capture, or in other words, we can say that the penalty that we get for using a imperfect model. Okay, so let's break it down to something. What is it about? To bring it in its simplest form. So what is my cross entropy? This is your minus sigma P of x log of qx, right? And what is your entropy? Sigma, that is your expected value of the same, coming from the same distribution. This is expected value coming from when the distribution and the prediction are same, and here the distribution and the prediction are different. So this is what is taking the difference. Now let's expand it. Okay, so here if you see that sigma px, this is common in both. Okay, and this is minus of minus, so this is negative term and this is the inherent minus, right? So this minus and this minus will become plus, so I'll just write it minus px log of q of x plus this minus and this minus, this will become plus because there is an inherent minus because of the surprise factor. Minus minus plus, this will be sigma p of x log of p of x, right? So take out sigma p of x as common and this will become log of px will come from here minus log of q of x, this will come from here. So log px, this is the plus, there is a negative sign, this is a log of qx coming here. So what is log a minus b? That is log a by b. So this is equal to, now you see this is a positive, earlier everything was negative and now you see this is positive, p of x log of p of x by q of x. So this is here KL divergence, this is how we write it. I hope the derivation is clear and the actual meaning behind what we do. This formula many of you will know, but this is the actual entropy and this is the actual understanding based on entropy. So it's a difference between the cross entropy and the actual entropy of the distribution. Cross entropy is when we measure a distribution using another distribution. So that's the delta, that's the measured surprise, right? This is the minimum surprise that the system or the model, or the distribution inherently has. Okay, this is your KL divergence. Let's, and if it is a, this is for our discrete. This is for discrete. Similar formula will hold for continuous. What will be continuous? So my KL divergence will be, this will become integral, simple, minus infinity to infinity. This will become px or f of x. Okay, log of, I'll let it be consistent, px by qx. So just the summation changes to integral. Okay, and this is just a summation. I can write I equal to 1 to n everywhere. Now the formula is clear. Let's do a simple example. So there is a note. There is something that, just note that KL divergence is not symmetric. Okay, KL divergence is not symmetric. What do I mean by that? That means that KL divergence of P when I measure it using Q is not equal to KL divergence of Q when I measure it using P. So this is not symmetric. This is one of the drawbacks. Because of that, we will study Jensen and Shannon divergence after this. Okay. So let's understand this. Just do the maths and understand it so that it becomes very clear. Let's continue the cat example. For example, continue the cat/dog example. What is that? Using the same. So what was that? Model is trained to classify. So my actual predicted value was that actual P was that 1.0 and this is 0.0. So this is for, this is the actual label, cat and dog. This I know, this is the truth or actual distribution. This is how it is. The probability of cat is 1 and probability of dog is 0. 1 and 0. This I know, this is the truth. And what was my entropy? Let me measure what is the entropy for this. Entropy would be minus sigma px log of px. So all the possible values of this will be 1 and 0, cat and dog. So this will be 1 minus 1 into log of 1 plus 0 into log of 0. Okay, so this 0 into log of 0 is undefined. Okay, just note that here, undefined, because that is minus infinity. Okay, but for approximation we take it as 0. For approximation we approximate this term 0 into log of 0 as 0. So this is a hack, computational hack that we do. But in actual terms, log 0 is undefined. So for computational hack, we'll say that computational hack. And in general, this entropy is measured in a computational hack that 0 log 0 is equal to 0 or log 0 is equal to 0. In general, whenever we measure entropy, we have a condition that sum of all the probabilities should be 1. So sigma of P of x should be equal to 1 in terms for entropy. That whatever are the possible outcomes of that event, the sum of that is the whole PDF or PMF, that should be 1. And generally the P of x is greater than 0, because we don't want to measure the values which are highly unlikely. Px equal to 0 where the probability is 0, which is a rare event or an impossible or highly unlikely. We don't measure these. So Px should be greater than 0. So that is where we measure entropy. But here, since we have encountered this, here we'll say that 0 log 0 is equal to 0, and we'll move ahead with that. So with this, what will this be equal to? This will be equal to log 1 is 0. Log 1 is equal to 0. We know that. We have seen from the graph also. This is equal to 0. So h of p is equal to 0. Okay. So now let's come back to model A. So what was my one? Model A. Model A predicted that 0.8 cat and 0.2 confident that it is a dog. So my KL divergence will be of P and Q will be equal to h of P comma Q minus h of P, right? This is my cross entropy. Cross entropy of cat and dog we computed earlier, right? 0.32 bits, h of P comma QA, right? It's for QA. So let me write it A everywhere. Okay. So this is 0.32 minus 0. This is equal to 0.32. Okay. So this is that model incurs 0.32 bits. Everything is in bits. 0.32 bits extra surprise, because the actual entropy was only 0, but the model QA prediction brought in this extra 0.32 bits of surprise. Okay, so this is what it means. And now the second model, model B. Model B predicted the opposite, right? That it is 0.2 cat and 8 dog. So this is your cat and this is your dog. Here this is your cat and this is your dog. Opposite. Similarly, what will be this? The KL divergence of P will be equal to cross entropy minus the base. So this we calculated 0. What is this QB? This cat and dog example we did earlier. Oh, this is here. 2.32 bits. Here we calculated this. Let's put that value because we have already calculated. So this will be equal to 2.32 minus 0. This is equal to 2.32. This is very, very high. Model B caused a lot of information loss because, as I mentioned, right, this KL divergence extra surprise or measures the information loss also. Okay, it measures the information loss also, and that will be measured in bits. So model A only caused 32 bits of information loss, and model B it is causing 2.32 bits of information loss, and this is what it measures. The higher means the model is far away from the actual truth. The prediction is far away from the actual truth. Okay, I hope KL divergence is clear with this formula.